Good morning to all. I am Dhanalakshmi, Assistant Professor, PG Department of Mathematics, Ict College for Women, Erode 12. Today we discuss the topic graph theory. Graph theory, fundamentals and applications. An introductory exploration of graphs, their properties and their role in modeling the world's most complex system. Graph, formal definition. A graph G equal to B, E is defined by a set of vertices V and a set of edges E connecting them. Vertices represent entities, people, cities, web pages or any discrete object of interest. Edges represent relationships or connections between entities, friendships, roads, hyperlinks. Foundation, the basis for modeling network structures and relationships across virtually every scientific domain. This slide, basic terminology. Vertex node, a fundamental point or entity within the graph, the building block of any graph structure. Edge, a connection linking two vertices representing a relationship or interaction between them. Degree, the number of edges incident to a vertex, a measure of how connected a node is. Path, a sequence of distinct vertices connected by edges tracing a route through the graph. In this figure, the degree of A is 3, degree of B is 2, degree of D is 3 and C is 2. Graph types, direct versus indirect. Undirected graphs. Edges carry no direction. The relationship between vertices is symmetric. Edge UV is identical to edge BU. Friendship network, road system without one-way streets. Directed graphs. Edges have an explicit direction represented by arrows. Edges U, V points from U to B and is distinct from B, U. Social media follows web page hyperlinks, task dependencies. Weighted graphs. Definition. In a weighted graph, each edge is assigned a numerical value, its weight representing a cost, distance, capacity or measure of importance. Weights transform the graph from a simple relational model into a quantitative one, enabling optimization problems to be solved. Social graph types. Complete graph. Every vertex is connected to every other vertex. For n vertices, there are n into n minus 1 by 2 edges, denoted kn. Bipartite graph. Vertices are divided into two disjoint sets. Edges exist only between sets, never within a set. Useful for matching problems. Tree. A connected acyclic graph. For n vertices, exactly n minus 1 edges exist. Trees are fundamental in data structure and algorithms. Connectivity and components. Connected graph. A graph is connected if a path exists between every pair of vertices. No vertex is isolated from the rest. Disconnected graph. A graph is disconnected if at least one pair of vertices has no path between them, yielding multiple isolated subgroups. Connected component. A maximal connected subgraph, the largest possible subgraph in which every vertex is reachable from every other. Cyclic and acyclic graphs. Cyclic means path starting and ending at same vertex. A path that starts and ends at the same vertex, traversing at least one edge. Cycles indicate circular dependence. Acyclic graph, no closed loops. Example, tree. A graph containing no cycles. Trees and directed acyclic graphs are canonical examples. Directed acyclic graph for scheduling. Applications. Cycle detection is critical for identifying deadlocks in operating systems and solving scheduling problems. Graph representations. Adjacency matrix. A 2D array where entry I, j equal to 1. If an edge exists between vertices I and j and 0 otherwise. Space complexity. Edge lookup. Constant time. Best suited for dense graph with many edges. Adjacency list. Each vertex maintains a list of its adjacent vertices, storing only existing edges rather than all possible pairs. Space complexity. O of vertex plus edge. Edge lookup slower than matrix. Best suited for sparse graphs with few edges. Criterion. Adjacency matrix. Adjacency list. Space. O of vertex squared. O of order of vertex plus edge. Edge lookup O of 1. O of degree. Best for dense graphs. Sparse graphs. Core traversal algorithm. Brief first search. Explores vertices level by level, visiting all neighbors of a vertex before moving deeper. Uses a queue data structure. Finds shortest path in unweighted graphs. Time O of P plus C. Depth first search. Explores as deep as possible along each branch before backtracking. Uses a stack. Detect cycles and connected components. Time O of P plus E. Dijkstra's algorithm finds the shortest path from a source vertex to all other in a weighted graph. Uses a priority queue, GPS routing and network optimization. Time O of V plus E log V. Real world applications and next steps. Social networks, modeling friendship, influence, provocation and community detection in platforms like Twitter and LinkedIn. Transportation, route optimization, traffic flow analysis and logistic planning using weighted directed graphs. Computer networks, packet routing, network topology design and fault tolerance analysis in distributed systems. Recommendation system, bipartite graphs connecting users and items, power personalized recommendation on streaming and e-commerce platform. Okay, thank you.